Okay, let's finish up the remaining examples in this current slide, this current chapter. So we had stopped here where we had seen this circuit. Let's see. Okay, we call this the positive side, not positive side. This is a limiter circuit, voltage limiter, and also said this is also known as a diode clipper circuit, right? This is a positive side limiter circuit because it clips or it cuts off the positive half cycle. And the reason it cuts off the cycle is because the diode is configured such that anytime the voltage or the input voltage goes positive, it turns the diode on. When the diode turns on, it starts conducting, meaning if you're trying to take the output across the diode, presents itself as a short circuit. So voltage goes to zero. You only have the output during the negative cycle. And so in the negative cycle, when the diode is off, V out is equal to V in, and hence we call this a limiter or a clipper circuit. There is a third name for this circuit, it is known as rectifier circuit. Anyone ever hear the term rectifier before? So diode rectifier, what, someone said something? No, not quite a bigger diode. So these circuits, as I said, we have a clipper, a limiter, or a rectifier. They are the same circuits. In some sense, the reason we call it a limiter circuit is because it limits the voltage either in the positive or the negative half cycles, right? So this is limiting the voltage in the positive cycles, and so it's a positive side limiter. On the next slide, we have the negative limiter or negative side limiter because we flip the diode, so now it turns on when the voltage goes negative, hence it's a negative side limiter. But it's also known as a clipper because it's clipping, right? We spoke about that. It's clipping. Now, if we take the output across the resistor, the same circuit is also known as a rectifier circuit. And rectifier circuits are one of the most important circuits or one of the most important applications of a diode. Rectifier circuits are the ones that actually convert AC waveforms to DC. Okay, so rectifiers, diode rectifiers convert AC to DC. And this is something that will come up in 315 or 3306. AC to DC is because it's only AC goes in both directions, positive as well as negative. As you can see here, you either have only positive or only negative. So it's only one direction. And then this is known as pulsating DC. It's not quite a flat line, but then we add a few more components to it. More specifically, we add a capacitor. The capacitor does the job of filtering out this so-called pulsating DC and gives us a almost flat line. Okay, but again, that's a topic for 315. Suffice it to know for now that this kind of diode circuit is known as a clipper, a limiter, or a rectifier. Okay, rectifier circuit. And we'll talk about the examples. Let's look at this example. So these next 2 or 3 examples hopefully will reinforce what we just talked about. So if you want to sketch the voltage transfer characteristic of this circuit below, we are using a CVD model. V in is on the left, V out is on the right. Okay. Oftentimes you see circuit diagrams drawn like this. The circuit diagram can be redrawn as okay. So what's the first thing you notice? 5 volts. What does that mean? Yeah, exactly. The cathode is connected to plus 5 volts. So if V in is less than 5 volts, is the diode on or is it off? If it's lower than 5 volts, diode is off. That means if V in is greater than or equal to 5 volts, diode is on. That's for ideal diode. For CVD model, if we assume either 0.6 or 0.7 volts, let's stick with 0.7 volts, right? Let's say this is 0.7 volts. If that's 0.7 volts, that means the anode must be greater than 5.7 volts. If the anode is greater than or equal to 5.7 volts, diode turns on, otherwise it's off. So with the CVD model, if V in is less than 5.7 volts, and the diode D is off. What is V out if diode is off? If diode is off, it is replaced with an open circuit. If it's open, then V out is equal to V in. Let's take a pause. Let me know if you have any questions. So far, so good. Okay. Then the next case is if V in is greater than or equal to 5.7 volts, then diode D is on. If diode D is on, then we have the voltage 5 volts and the constant voltage drop across the diode of 0.7 volts coming directly across the output terminals. And so V out would be a constant line of 5.7 volts. That's it. That's the answer. So 5.7 volts, let's say mark it approximately here, 5.7 volts. That means as long as V in is also below 5.7 volts, and let's say approximately here at that line. Beyond this, it's a flat line of 5.7. And then that's how it is. If V in is 0, V out is 0. If V in is -1, V out is also -1. If V in is +1, V out is also +1 until V in exceeds or equals 5.7 volts. From that point on, V out is 5.7. So here, in this range, V out equals V in, and here, V out equals 5.7. All right, let's take a pause. Let me know if you have any questions. Do the steps make sense? Anytime you're faced with diodes and we're analyzing with either ideal diode or CVD model, we only have two states, whether anode is higher than cathode or lower than a cathode. If it's higher, diode is on, you replace it with a short circuit. If it's off or it's lower, then it's off, you replace it with an open circuit. In a CVD model, off is still open. In the forward bias, it's not a short, simply a voltage source of 0.7 volts. That's all we do. All semiconductor devices like diodes, transistors, they all use different kind of models for different applications. Once you have applied the model, from that point on, it is simple circuit analysis. The same circuit analysis that we have done. Okay, Ohm's law, KVL, KCL, they all still work. All right. Yes. Um, is the what? Yes, is 0.7. That's just provided to us. Oh, question being asked, why does it combine? Is because the diode is connected this way. So the anode is here. Positive reference is at the anode, plus and minus. So when the diode turns on, it'll be a voltage drop. Actually, let me do it here. When it's off, it's an open circuit. That's clear to everyone, correct? Right. So when it's on, a diode is replaced with a constant voltage source of 0.7 volts. That's the constant voltage drop model. And since the anode is positive, the positive terminal of the source is where the anode is connected. So when we have replaced the diode with a voltage of 0.7 volts, that 0.7 volts is in series with the other 5. And that's why they're added up. Does that make sense? Does that answer your question? That's why it is 5 plus 0.7. If we flip the diode, what would be the voltage required to turn it on? Which I would assign a student practice, but let's say yep. If it's like this, then what is the voltage at the anode? 5. Sorry, yeah. Let me write a voltage of the battery. Yes. So the anode is held at 5 volts. That means the diode cathode needs to be below 5 volts. So as long as V in is below 5 volts, the diode will be on. And when the diode is on, Let's say in this case, the voltage would appear like this. And if I was to take V out here, this V out, you can apply KVL and mathematically write any expression, but of course, this would simply be 5 minus 0.7 or 4.3 volts. Because this would be 0.7 in opposition to that 5-volt source. Yes. Good question. So what happens if the voltage source is flipped? And then that would be for students to analyze and understand. But yes, that is correct. To extend your learning, I would say you have two possibilities. You can flip the diode or you can flip the voltage source. So you have a 2x2 matrix, 4 different scenarios. You can work through these manually and then verify your answer with LT Spice. Okay. All right. We have about 5.5 minutes left. We have 3 more slides to cover. So I'm just going to move on to the next one for now. You have 2 voltage sources, not voltage sources, 2 diodes. And so right now, what do? You can analyze each branch independently. So we had this branch, we had already analyzed that. Now we also have another diode. The diode is facing in the opposite direction. So we'll analyze it differently. Now, if we use the CVD model, and let's say CVD model with 0.7 volts, I'll go a little bit quicker because we only have a few minutes left. CVD model with 0.7 volts. Let's analyze what happens when V in is less than 5.7. We are starting with 5.7 just because we solved or analyzed this branch previously, right? So we already know that there's a condition that requires the diode to turn on. So if V in is less than 5.7, what can we say about diode D1? We just saw it on the previous slide. D1 is off. What about D2? D2 is also off. So less than 5.7. The anode of the anode of diode 2 is held at the reference point or ground, which is 0. If the anode is at 0, that means the cathode must be negative. It has to be below 0. Otherwise, the diode would not turn on. So if V in is less than 5.7 volts, diode D2 would be off. But if it's below 0 volts, which is not specified, then diode D2 would be on. We don't know that yet. And that would be the second condition. If V in is less than minus 0.7. Again, D2 can only be on if the anode of D2 is less, the cathode of D2 is less than 0. That's for ideal diode. In CVD model, it must be less by 0.7 volts. If the anode is at 0, the cathode of D2 must be less than minus 0.7 volts. So that's the second condition. D1, of course, will still remain off, but D2 is now on. Quick pause. I want to make sure everybody understands that second statement. Does everybody understand what I just said? We started at 5.7 because we analyzed D1 in the previous example. So we knew at 5.7, D1 is going to be off. When we look at D2, we can see anode of D2 is connected to 0, which is right here, 0 volts. And because that this is at 0 volts, the cathode must be lower than 0 for it to turn on. With the CVD model, there must be a difference of 0.7. That means cathode of D2 must be less than minus 0.7 volts in order for it to turn on. That's the second condition. So if V in is less than minus 0.7 volts, D1 is still off, D2 turns on. If D2 turns on, it behaves like a constant voltage source of 0.7 volts. And if we take V out across those terminals, which is right here, then your V out is equal to minus 0.7 volts. Okay, minus 0.7 volts. And of course, the third case is where V in is greater than 5.7 volts, which is something we already saw previously. Then D1 is on. D2, of course, is going to remain off. And then V out is 5.7 volts. We're not going to get to the next example today. So we'll slow down. All right, line at 45 degrees. Let's say 5.7 here, 5.7 here. This is V out equal to 5.7. And then this is not to scale. This is V in equals minus 0.7 volts. And so V out is also minus 0.7 volts. Oh, shouldn't be like this. Not quite passing through the origin, but that's how it should look. The only difference is that we have D2 connected in there, and because of D2, it conducts when it's less than minus 0.7 volts. So when V in goes negative, diode D2 turns on, and because diode D2 turns on, the output is now held constant at 0.7 volts. All right, we'll end class here today. We'll pick up here again for the last two examples on Friday. If you have any questions, I'm happy to answer them.